Hello and welcome to the Daily Space for today, Blur's Day, May 7th, 2020. I am your host, Dr. Pamela Gay, and I am here to put science in your brain. Today, we are going to be joined by PSI senior scientist, Dr. James Richardson. Jim, we're going to call him Jim. Last week, we discussed his recent research highlighting how shaking and tiny impacts slowly erase the surfaces of even tiny worlds like the asteroid Eros. This is work that affects the science we like to do here on CosmoQuest when we're actively mapping craters and, well, other features on planets, moons, and asteroids. Since this work is that near and dear to our hearts, we've invited Jim on to take a deeper dive into crater erosion. But before we do that, let's take a look at the news. Today is one really slow news day. But what it lacks in diversity in science, it makes up for in lift. Our first story is related to rockets that, managed to evade making it into yesterday's Rocket Wednesday roundup. On Tuesday night, SpaceX's SN4 test version of its Starship was finally able to successfully sustain the pressures of being filled with fuel, and from there, it went on to survive the firing of its single Raptor engine. Starship will be the topmost stage of a new launch system that will dwarf even the Falcon Heavy and SLS's planned Block 2 cargo rocket, and it will have a mighty 150-ton lift and stand 150 meters tall. Now, SpaceX has conveniently placed their rockets where they can be beautifully imaged by folks with telephoto lenses working off property. One of the best people to follow doing this is Boco Chico Gal. In her video of the test firing, SN4 can be seen slowly getting covered in frost, and then steam and mist rise up from beneath the prototype as a sound suppression system is engaged. Moments later, the engine kicks in, adding light and billowing steam and possibly stirring up dust to fill the Texas night. We are going to take a look at a clip from this video. We're going to try and take a look at a clip from this video. There we go.
Yeah. All right, so the sound suppression system's on.
Is that the first time we've seen that? I don't recall them having a sound suppression system or a fire suppression system. We have ignition! Blocked out all the light.
Ignition and shutdown.
So the voices you may have been able to hear in the background were John Galloway, who goes by Das Valdez here on Twitch, as well as his co-host, whose name I couldn't readily find. And again, this is video by Boca Chica Gal. Now, a much smaller version of Starship, the Skyhopper, has previously done jump tests, and now SpaceX is working to scale up their systems. They have plans to one day use this rocket, to put humans back on the moon and carry them in large numbers all the way to Mars. Now, until this week, Starship was a personal project for SpaceX, something the company was designing as they pursued their corporate goal of, like I said, putting humans on Mars in large numbers. That all changed in a small way last week as NASA announced which companies will receive funding to develop vehicles capable of returning humans to the moon in just the next couple of years. SpaceX is one of 3 teams selected to receive initial development funds. The other 2 teams are Blue Origin, which is billionaire Jeff Bezos' company, and Dynetics. Now, if you haven't heard of Dynetics before, you aren't alone. This often forgotten group is a subsidiary of Leidos and also gets lost with its collaborators like Boeing, who are working together to deliver the space launch systems. In addition to working on Artemis, Dynetics is also contracted to deliver the Space Launch System's core and upper stages, as well as the Orion multipurpose crew vehicle. For these companies to succeed, they're going to need to do a number of test launches in just the next 24 months, all in the lead up to putting, according to NASA, a crew of all women on the moon by the end of 2024. Now, given the current delays that we're seeing in space launch systems, given that Blue Origins currently lacks a human-certified vehicle, and SpaceX is, well, generally random when it comes to following timelines, I'm not sure anyone is confident in NASA's timeline. But whenever humans do return to the moon, we'll bring it to you right here on the Daily Space. Now, I think I mentioned it's a slow news day. That's really all we've got. But this doesn't end our episode. In just a moment, I'll be joined via Zoom by Dr. Jim Richardson, a PSI scientist who is part of numerous missions studying rocky worlds of all sizes in our solar system. We're going to be talking about crater erosion and how it affects worlds as small as Eros. So don't go anywhere. We will be right back in just a moment. Hello, everyone, and welcome back. And thank you so much for joining us, Jim. Where are you coming to us from today?
I'm coming to you from South Bend, Indiana.
That is awesome. And for those of you out there who are noticing that his feed is a bit blurry, I will remind you it's Blur's Day. His camera decided to join in on everything just being a little bit fuzzy. We've tried to fix it, and it's done. It's 2020. The camera, it's with us. So you have been studying how craters literally impact the surfaces of worlds all over our solar system. How is that something you get into as a career? This is one of those questions I get asked all the time around here.
Okay. Well, I was an amateur astronomer for going back to age 12. And in the 1990s, I had reached a point in amateur astronomy where I was making contributions to the American Lunar and Planetary ALPO Observation Society, also to the American Meteor Society. So I already had an interest in small solar system objects, and in that instance, it was shooting stars entering the upper atmosphere. And I had a chance to go back to school and actually turn amateur astronomy into a career in planetary science. So I went from very tiny dust particles, meteors, to somewhat larger objects, objects in the main asteroid belt, going all the way down to tiny grains. And at the time I was in graduate school, the Near Shoemaker mission orbited asteroid 433 Eros. And the images brought back from Near Shoemaker were absolutely spectacular. And there were some interesting science questions that were left over after that mission completed in 2001. So I picked it up as a dissertation project, and that's what got me into impact cratering and all the surface processes related to that, especially on very tiny worlds. My advisor is Henry J. Malosh, who wrote the book called Impact Cratering that we use in our field quite a lot. So I had a very good advisor in that regard, and then went from there.
So you lived the dream. You went from being just an everyday adult human doing amateur astronomy, looking up in your spare time, to figuring out how to make this your day in, day out reality.
Mm-hmm. Well, I turned lemons into lemonade, because in 1993 I was a nuclear power plant operator. And I was involved in a chemical injury where I lost most of my eyesight. And because you can't be a blind nuclear power plant operator. I had the opportunity through the Florida Division of Blind Services to go back to school and start a whole new career. So I was able to take, the loss of most of my eyesight and turn it into a new career, doing what I'd always wanted to do in the first place. It worked out really well in that regard.
That's absolutely amazing. Now, your science is why we have you here today. When we're out looking at other worlds, I don't think there's such a thing as an object that doesn't have at least one crater on it. And when we have a whole myriad of craters on a planet, we find that when we can figure out this one's younger and that one's older, they don't appear exactly the same, but these worlds don't exactly have wind or rain or any of the normal things that would cause craters that are young and old to have different looks. Can you take us through and explain what exactly is going on here?
Well, there's a couple of things to keep in mind. First off is scale. So when you look at the surface of the moon, for example, unless you're looking at very narrow angle views from like the Lunar Reconnaissance Orbiter, for the most part, you're looking at craters that are tens of kilometers in size, which are much better preserved. I mean, the lunar upper highlands has cratering history going back to 3.5 to 4 billion years ago, and a lot of that has been preserved relatively intact. When you look at something like a small asteroid, you're looking at a surface that's the same age, but the size scale is much, much smaller. Craters of 100 meters in size, or up to a couple of kilometers in size, and even smaller. And those smaller craters are much more easily affected by whatever erasure processes exist on the surface of that body.
So essentially, it's craters all the way down, but the smallest craters tend to get stomped on by the bigger craters.
Right. Even on the lunar surfaces, the smallest craters get erased much faster, and therefore, to resurface it in new craters, we're looking at a much more recent time history on those time scales. Now, something like the asteroid Eros is somewhat unique in that it spent most of its lifetime out in the main asteroid belt, being impacted there, and then about 50 to 100,000 years ago, it entered into a resonance zone with Jupiter and was kind of injected into the near Earth asteroid environment inside the orbit of Mars. And that kind of froze its cratering record in place from the time that it was out in the main asteroid belt, because where it is now, the impacts are a lot less frequent, about 1/100th as frequent as they were out in the main belt. So that's another thing to kind of keep in mind.
And so let's just think about that one for a moment. Here on Earth, we all see meteorites now and then, and thanks to the proliferation of dashboard cameras, there are some truly amazing videos of bolids, meteors coming through the atmosphere. We know rocks are falling on us from the sky. And when we look at the moon, sometimes we're lucky enough to catch flashes of light from these impacts. But you're saying that what we experience is 100 times less than what we'd experience in the asteroid belt?
Yes. Right. The asteroid belt is a collisionally evolved population. So it's constantly things are constantly colliding with other things in the main asteroid belt. And then you also have things that are being filtered in toward the inner solar system from the main asteroid belt. So the particles that make up and the objects that make up the near Earth asteroid environment, at some point, either they or their parent body was most likely part of the main belt at one time in their lifetime and been migrating inward since then. So things in the asteroid belt are constantly colliding with each other, forming new asteroid families, breaking up into smaller bits, smaller particles, and every now and then one of those will enter into primarily the resonance zones in the main asteroid belt with Jupiter. Kirchhoff gaps and resonant areas like that will alter the orbit of that asteroid and make it and cause it to become a near-Earth asteroid at that point. So there's a constant filtration of objects coming in from the main belt into the near-Earth environment. And they either collide with something in the near-Earth environment, or they enter the sun, or in some cases are ejected from the solar system. See, there's the cat.
Cats are welcome. So does this mean that we can blame Jupiter for Bennu?
I don't know Bennu's history, so I'm not sure. I'm not entirely sure how it entered the near Earth environment. We do know that it's a C-type asteroid, and those do have, I think, their roots primarily in the outer main belt. So, but I don't know. I'm not a dynamicist. I'm not sure exactly how Bennu got to where it currently is, but most likely its parent body began life in the main belt and has made its way into the near Earth environment.
That's all good. We're just always looking for somebody to blame for Bennu because that object is just rocks on rocks on rocks. But Eros is a much more beautiful object. It's kind of cashew shaped. I think you even have a model there of it.
Yep, I gotcha. Yeah, it's kind of a bent ballet slipper to me, but
oh, I see.
A lot of people give it very different interpretations as to the shape. But yeah, this was once part of a much larger body. And what we have now, like I said, lived in the main belt for most of its lifetime, is now a near-Earth asteroid. And so the cratering record that you see on it, like most prominent crater, I don't know if you can see that little dimple there, yep. That's Psyche crater. Then there's also a big concavity on this side that's called Himros. And then there's another weird region, if I can feel it here, right about here, that's the Schumacher Regio. So just to give you a scale, this asteroid is about 30 kilometers in length, about 12 kilometers in width. Himros is about 10 kilometers across. Schumacher Regio is about 8. And little Psyche here is 5 kilometers. And from there you have a handful of 1-2 kilometer craters and then a whole bunch of smaller ones. What got me interested in the current project that we just published on it was the fact that when you go down to the very smallest crater sizes, Eros appeared to not have enough of them. When Yarkovsky visited in 2000, 2001. And there were 3 main explanations. Number one was that maybe there aren't enough small impactors in the main belt, not as many as we thought there ought to be, based on that collisional grinding I told you about earlier.
Right.
There should be lots and lots of really tiny impactors, so there should not be a deficit of little craters on Eros, but there it was. The other explanation was that Eros has a lot of boulders on it, which I guess you and your crew are quite familiar with on Bennu.
Yep.
So one explanation was that maybe those boulders kind of shield the creation of small craters, but the boulder density is not nearly high enough for that to be a viable explanation. The third explanation was that those small craters are being gradually erased through seismic shaking or asteroid quakes. So each time you get a new impact, will most likely cause a global seismic event on Eros. Anything from 1 meter diameter impactors and larger will produce a global seismic event. And because the gravity is so tiny, 5 millimeters per second squared, as far as the acceleration on Earth, it's like 9.8 meters per second squared for the acceleration of gravity. It doesn't take much to destabilize the slope and slowly cause the regolith layer on the outside of the asteroid to soften and then fill in small craters, so to the point that the equilibrium level of those craters is lower than you would expect, causing that deficit in small craters. And I did that 10 years ago now 15 years ago for my dissertation project. I did some modeling work to show that how that process worked on Eros.
So let's try and unpack this a little bit. The first thing I want to start with is you said that out in the asteroid belt, there are essentially constant impacts. Now, you're not saying that things the size of Vesta are slamming into things the size of Ceres on a regular basis, but there's actually like a rate of cratering that has big craters forming more rarely than tiny craters, I think. Can you explain
exactly
that?
Right. Exactly right. Well, it's a very steep distribution. So you have, like in a simulation for Eros, I may have, a few million impacts that I simulate in the model. The vast majority of those are very tiny impactors, from a decimeter or so up to a few meters in size. But where the tiniest ones, the decimeter size impactors, are the most numerous. And as you go up to larger impactor sizes, the the number of those impacts drops off exponentially. It's a power law. And something like the crater, something that would cause this crater Psyche on Eros, this guy here that's about 5 kilometers. A crater like that will form only about once every 500 million years or so out in the main belt where this thing lived. So these kind of impacts are very rare. Or the tiny impacts, you'll have several hundred per million years or so on Eros when it lived out in the main belt. Now they occur much, much less frequently where it's currently at in the near Earth environment. Still there?
Sorry, my dog started whining. So you did some simulations of this. Would this be a good time to show one of those simulations?
Well, let me just, So rather than simulating cratering on something that's oddly shaped like this, which is difficult to do in 3 dimensions, the computer model that I have actually turns this surface into one smooth, continuous, flat surface without all the bends and the weird shape and the gravity. So if you want to do that first color figure.
So I currently have the color figure that is predominantly yellow. Is that the color figure you want?
Yeah, that's the one.
Okay.
So what this is a simulated asteroid surface. It begins as a flat bedrock surface with the Eros gravity magnitude, so 5 millimeters a second squared across the entire surface. I have to tell it what properties to apply to the target rock, how strong the rock is, what the gravity is, what its density is, and then from there, I'll select randomly impactors from a main asteroid belt impactor distribution. So randomly sample or Monte Carlo sample from that impactor population. The computer will pick a random spot on the surface. It'll plug a random impactor, its size, its own, and its speed, and even the impact angle is varied. And when it strikes the surface, we produce a model crater on the surface, and then let those just build up over time. So that figure that you're showing is the topography that results from about 500 million years, 400 to 500 million years of exposure to the main belt for a model surface that's the same surface area as the size of Eros. And you see I got one nice, hemorrhoid size impactor. That's the dark blue region.
And so this is really capturing that difference in frequency as a function of size for all the things coming in. Now, we're getting a bunch of questions from the audience that I'm going to bring up that they're super excited. Like I said, they love asteroids. So Henny asks, does the Yarkovsky effect lead to a lot of debris in the asteroid belt?
Yarkovsky effect primarily affects near-Earth asteroids because they're much closer to the sun. Once you get out to the main belt, the Yarkovsky effect has much less effect. For example, as part of his work, I have a dynamicist who, David Minton, who was part of the work, and he was actually looking at Yorp and Yarkovsky with regard to asteroid Steins, 2867 Steins. And what we wanted to know was, especially with regard to the Yorp effect, which is related to Yarkovsky effect on Steins, how often is it spun up or spun down? Because it has that same kind of a blade top shape that Bennu has and Ryugu has. But right now, its rotation period is kind of an optimal rotation state. It's not a fast rotator. So what we wanted to know with regard to the modeling was, if it's spun up, then that's going to cause its own form of crater erasure as things migrate down towards the equatorial bulge. And we discovered that out where Steins currently is, that effect is very, very slow on the lifetime, on a scale of 600, 700 million years. So the further you get out into the main belt, the less effect Yarkovsky and York will have on the body. But when you get into the near-Earth environment, those become very important, especially for things less than 4 or 5 kilometers in diameter and below.
Okay. Now, while the effect isn't getting things pushed out into the asteroid belt, You mentioned that getting things out of the asteroid belt can happen when objects are dynamically driven by interactions with, for instance, Jupiter. Now, Ark asks if there are more violent ways for getting things our direction. For instance, do any of these collisions that take place send things flying into the inner solar system? And how massive of an impact would be needed to knock an asteroid from the belt into the inner solar system?
For the most part, these things are on orbits that, they're traveling tens of kilometers per second in their own orbit. So a collision between two objects in the main belt will produce a new asteroid family. Like say you have something that's 100 kilometers in diameter and it collides with something that's similar in size. You can produce a new family, but that entire family of objects will generally stay dynamically in the same relative area. We've actually have a couple of examples of relatively recently formed families. We can actually see the scatter of those objects within that region of the main belt. So they don't travel very far away from where they originally were, because they're still all orbiting the sun at that same distance. But they will spread, and there will be some size sorting. And the older the family is, the more diffused that family of objects will be within the main belt. And if they diffuse out to a part where they enter into a resonance zone with Jupiter, then they could be thrown into the near Earth environment.
Now, to go back to your simulations again, one of the folks in our audience, Don't Drink, says, could you talk about the math behind your simulation? They ask, is this a stereographic projection? Exactly how did you define the asteroid as a flat surface?
The flat surface actually it's in a way, you can't actually represent it in 3 dimensions because it has what's called continuous boundary conditions. So the left side of the simulation, the right side of the simulation will wrap around and touch each other. But also the top and the bottom of the simulation also wrap around and touch each other. So it's an MC Escher-esque type object, a Mobius type object. And so I actually can't take my simulation and wrap it around to form a 3-dimensional shape. But what that means is I can actually choose the resolution of the simulation to where the surface area represented by the model matches the same surface areas as 433 Eros in this particular case. So we'll have the same gravity, have the same, hopefully, rock target properties, also the same surface area, and then the same impact of population. So that's how I can do it as when I say flat, it's not actually flat because of those continuous boundary conditions. It's wrapped around both top and bottom. You can kind of see that in that image that you're presenting, where it wraps around from left to right with a very large crater with the blue colored bottom on it.
And so looking at this image, while it doesn't represent the exact aspect ratios of Eros, it has the same surface area. And since asteroids are rotating, you kind of assume that where you are in the asteroid doesn't affect how much impacting you get for simulations like this?
The rotation will affect the gravity. So on Eros, the regions, like I'm going to pop things around here. The regions on the end have a gravity around 2 millimeters per second squared, while regions toward the center area here the waist will have a gravity around 5 or 6 millimeters per second squared. So it does affect the surface gravity quite a bit. What I do in the simulation is I choose the mean gravity for the body and apply that across the entire surface. So what the model is doing is actually kind of representing the mean surface properties of Eros without including all the small variations that occur along the way.
Now to get back to the science that you've been doing, what you noticed is this object just doesn't have all the small craters that you would have expected given the population of stuff raining down upon Eros. And the solution that you came up with is one that I've previously heard for the moon, and I just hadn't thought about applying to asteroids. So you mentioned earlier that seismically, you shake these things and it smooths out the little craters. Can you go into that a little bit more?
Yes. Okay. Well, we just go ahead and run the first simulation, the animated GIF for 433 Eros.
Okay.
And I'll talk as we watch that.
This is going to take me just a second to get back up on the screen. Hold on. All right, it's running.
Okay. Like I said, one of the theories about why we have a deficit of small craters and Eros is that each impact will cause a seismic event on the body. The tiniest impacts of objects less than a meter in diameter will cause a local seismic event, while things a meter or two and larger will cause a global seismic event. And so what happens is that as each new impact occurs, especially near that impact site, you'll get a seismic shaking event that will cause the regolith layer on the outside of the asteroid to slowly migrate downhill. So like a small crater that begins with a regular 1:5 ratio between its depth and its diameter will slowly degrade, the rim will degrade down, and the bottom will slowly fill in until you flatten to the point you can't recognize the crater any longer. And you can, if you look at the smallest craters in that simulation, you actually see that process happening.
Yeah.
The bulk of the paper concern how you actually estimate the amount of seismic shaking you get as a function of distance away from each impact, and then how that affects regolith motion on the surface. So we put a lot of energy into modeling that correctly, not just for Eros, but for asteroids of a variety of sizes. But because I'd done Eros previously, and that model there was just for Eros in particular. It couldn't really be applied to other asteroids. I had to match this new model, make sure that it fit in my previous results, and the previous results did not use this full three-dimensional terrain cratering model, and now we actually can do that for Eros. So that became the first object that we looked at. So in the simulation, you actually can watch as a fresh crater forms. You have a nice sharp rim and a nice good depression for the bowl. And then over time, it slowly degrades away just due to seismic shaking. You also have new impact craters that form on top of that. So little craters will what's called sandblast larger craters and erase them that way. And then larger craters can actually erase an entire population of smaller craters in a process called cookie cutting. So you have several different erasure processes, including seismic shaking.
Now, this is the kind of effect that has previously been recognized on the moon, and the moon and Eros have exceedingly different gravity. On which world do these things erode away faster?
Well, seismic shaking on the moon only affects primarily the region right immediately around the crater, out to 1 or 2 crater radii at the most. Except unless it's a really, really large basin-forming impact, then you can have antipodal shaking on the opposite side of the moon from the impact. So the super large basin-forming impacts on the moon will cause large seismic events there. The small impact craters in the moon do not, because the moon's gravity is 1.6 meters per second squared. It takes a lot larger impact, and you have to be a lot closer to the impact to overcome the gravitational force that actually caused stuff to migrate down slope. On Eros, it doesn't take much at all to overcome the force of gravity, and that's why seismic shaking is much more prevalent there. If you want to go to the next simulation, and we'll look at little 5-kilometer diameter asteroid Steins. So now we're just a fraction of the size of Eros, and you can see on Steins that seismic shaking is much, much more efficient. At erasing even large craters there. The crater does not last long on Steins, and whereas on Eros we saw a deficit of craters less than about 100 meters and smaller is where you had your deficit of craters on Eros. On Steins, it's 500-meter craters, 5 times the size and smaller. So its crater curve is very steeply it goes down very steeply, especially as you go down from large craters to smaller crater sizes. And that's almost entirely due to the effect of impact-induced seismic shaking. Because although their interior rocks, their interior structure have relatively similar seismic properties, which is one of the findings from this work. Because what I can do is I'm trying to match the cratering record, and by tweaking the seismic properties of the body until I can reproduce the cratering curve. So the crater curve, the crater counts become my ground truth that I'm trying to match. And now that we've included seismic shaking in the model, I can slowly dial in or dial up or dial down the seismic properties of the body until I exactly match the cratering curve, and it tells us about the seismic properties of the body itself.
That's all kind of amazing. And in looking at this with Eros, you have so many different puzzles to sort out, because there's the historical change in the impact record from when it was in the asteroid belt to when it was a near-Earth object. And how do you go about simulating that kind of a step function and how much it's getting whacked around?
Well, in order to compare apples to apples between Eros and then Steins and then finally little tiny Itokawa, I expose all of them to the same impactor flux. So now Steins is out in the inner main belt, so it's already part of the main asteroid belt now, and it remains there today. Eros used to be part of that. Little Itokawa was not part of the main belt. Its parent may have been, but currently Itokawa, as we know it, was not. But in order to look at the seismic properties of the body, I actually don't try to exactly simulate the time evolution for each individual asteroid as it actually occurred. I essentially hit them with the exact same impactor flux. That way I can look at the crater properties and the seismic properties and compare Eros to Steins to Itokawa, one after the other. So I actually don't duplicate the time history of how the impactor flux changed. So the ages that I get, for example, like for Itokawa, it takes my simulation about 20 million years of simulated time to match the crater record on Itokawa. But that's as if I'd thrown it out in the middle of the main belt. Where it's at now, it would take about 100 times longer. So about 2 gigayears, 2 billion years to reproduce that exact same crater record for little Itokawa where it is now. So it's kind of something to keep in mind with this work. I'm trying to compare seismic properties and crater records, so I actually compare apples to apples with each one and hit them with the exact same collection of bullets, more or less.
And Itokawa is a super tiny little asteroid. Up until we started sending things to Ryugu and Bennu, it was the smallest one we'd really explored. And wow, were we confused when we got to Bennu and it didn't look like Itokawa. Can I pull up the simulation that you did for this one?
Yeah.
Okay.
Mm-hmm.
I almost...
Got some water too.
Okay. So I'm ready to have it on screen whenever you're ready.
Oh yeah, go ahead.
There we go. Okay.
The interesting thing about Itokawa is because it's so tiny, it has such a small volume, and its gravity field is about 0.1 millimeters per second squared. It's an extremely tiny gravity field. It doesn't take much at all to cause a global seismic event on Itokawa. Something like a 3 or 4 centimeter impactor will cause a global seismic event on Itokawa. So that's kind of on the plus side as far as how effective seismic shaking is. On the minus side, Itokawa is an obviously recognizable rubble pile asteroid. Whereas something like Eros is what is called a fractured monolith. It has a global fractured structure which caused ridges and grooves to be visible across the surface. But the overall structure, the main fracture blocks are much larger, and they remain more or less intact or in place where they were when the fractures all occurred. Something like Itokawa has obviously been disrupted and then aggregated gravitationally. So it's much more of a jumble, and therefore seismic energy has a lot more trouble propagating from one side of Itokawa to the other because things are not coupled very well or connected very well. The tiny gravity also makes that coupling that much more difficult. So seismic energy, it takes a lot more seismic energy, relative to like a small space to actually propagate from one side to the other. Eros wants to attenuate and reduce that seismic energy quite a lot as you go from one side to the other. But its tiny volume means that the energy has nowhere else to go, and a tiny gravity too to move things around the surface. So regardless of how ineffective the interior is at transmitting seismic energy, The outside still is highly susceptible to seismic shaking and crater erasure, to the point that things, it's like, if you look at the animation, it's like dropping, rocks into a mud puddle. The craters just don't last very long on the surface of Itokawa at all.
Now, what's the time scale on this?
I think each time step in that animation is 10 to the 5th years.
So 10,000, no, 100,000.
1,000 years per time step.
Yeah, 100,000 years per time step. So
that's out in the main belt too.
Right.
And so it's 100 times longer if you put it into the near-Earth environment where it's currently at.
Okay. So
on Itokawa, the largest craters that you can form without disrupting the body is around 100 meters or so. Those last about 10 to 15 million years if Itokawa were out in the main belt.
Okay.
Very tiniest craters that are a few meters across will last around, well, in the simulation, last about 1,000 years. But again, multiply that by 100. So 100,000 years to erase something that's a few meters, a crater that's a few meters across Itokawa.
So you referred to Itokawa as a rubble pile asteroid. And as far as rubble piles go, it's pretty friendly. It has a lot of nice, smooth areas that are coated in what appear to be dust or fine-grained materials. It's got nice, smooth surfaces. Now, when we're looking at things like Ryugu and Bennu, there's not a whole lot of dust. It's a whole lot of pebbles and boulders on pebbles with pebbles on the boulders. With this less fine-grained material, I'm asking you to speculate wildly here. How does that affect the ability to erase the few craters that are there?
Based on the small size of the object, I would still expect seismic shaking to be a key factor in erasing craters on something the size of Ryugu and Bennu. At the same time, the material properties of a dark carbonaceous body are very much unknown, other than the carbonaceous chondrite meteorites that we have on Earth. I've actually, up until this point, have kind of shied away from even wanting to model something like that until I have a lot more ground truth, and hopefully Hayabusa 2 and OSIRIS-REx will give me a lot more information with regard to what are the material properties of the surface, so I can actually model something like this. Because the model, I've done an S-type asteroid with Eros, silicate rock body with Eros, another silicate rock body with Itokawa. Steins is an E-type asteroid, which is pushing it towards the metallic or the heavier rock type range, much higher density. It's still very, standard rock-like properties that we can model with some confidence. Something like Bennu and Ryugu has a lot more unknowns, and these are all parameters I have to feed into the model. I have to feed in the actual physical properties of the target body itself, including the rock strength, assumed rock strength for the body, and so forth.
Yeah. And
the further I get away from something that we actually have hand samples of on Earth, and something we studied on the Moon, which is another silicon type body, the further we get away from that, the more speculative you have to become. And so I haven't modeled Bennu or Ryugu yet, and I'm not sure that we'll have to see what we learn from like sample return and so forth from each one before I have some confidence in modeling it properly. The other thing is, for Eros and Itokawa and also Steins, I was able to use the lunar surface as a seismic analog for how the asteroid's going to behave, because the upper lunar crust is, again, silicate rock, highly fractured, and we actually put seismometers on the ground there and actually studied meteoritic impacts through those seismometers. So I actually know a lot of the properties of that type of silicate rock environment in an impact environment. Now, granted, a much higher gravity environment than on the asteroids, but I actually have something to start from with regard to how do I go from the lunar surface to an asteroid surface. Now, it turns out that Eros and Steins, their internal seismic properties are about 1/10 to 1/100th of that of the Moon with regard to how well they propagate seismic energy. So they attenuate the seismic energy by a factor of 10 to 100 compared to the lunar surface. Itokawa, it's about 1/100th to 1/1000th as efficient at transmitting seismic energy compared to the lunar surface. So I'm getting the 2 or 3 orders of magnitude away from the lunar surface, but I'm still within shouting distance with regard to my confidence in how well I can model that internal structure as far as how it propagates seismic energy. Something like a C-type body, it would just be a wild guess at this point, so I haven't even tried it yet.
Yeah, and I'm really looking forward to seeing how this science plays out in the coming years. I mean, for all we know, Ryugu and Bennu are going to be more like the Brazil nut problem, where you shake them slightly and the big things rise to the surface. There's so many different possibilities because we just don't know what are the materials, and is it boulders all the way down that have these same just several meter size scales to them.
The other thing affecting them, and I don't know if you talked about this with your folks in the past, is that with that oblate top structure and their small size, they're highly affected by York's spin up and spin down. So they'll spin up and then they'll spin down, and as they spin up, the slopes on the side are at near the angle of repose. So you have a constant migration of material, from the polar areas toward the equator to form the equatorial bulge. And actually occasionally will spin off, at least according to some of the theorists, will spin off and form small satellites like the one around KW4 or around Didymos that's going to be hit by the DART mission. So you have that constant downslope motion from the poles toward the equator, which also will erase any impact craters that form there. And if the entire thing is formed out of cobbles and larger boulders, then the downslope regolith flow in that case is a lot more constrained because things will interlock with each other and interfere with each other. And that large boulder has a much larger surface area for frictional locking to occur. So it's going to hamper the downslope flow of regolith in that respect as well. So again, I'm not ready to model something like that because there's just a lot that we don't know yet at this point with regard to how those things behave over some period of time.
And this is why we keep doing science. It's because there is so much that we don't know. And as soon as we have some starting points, it's time to figure out what we can learn. And it's kind of awesome. Now, we have some more questions coming in from our audience. Don't Drink is saying, I want to enter a PhD program in mathematics, and I'm currently an incoming freshman math major. Do you guys have any advice on how to set myself up for the best programs? So my personal advice is learn how to program while you're doing math. Figure out Mathematica, MATLAB, one of those things, and then see whose research you can get involved in. There's a whole lot of people who just need a smart student with some computational skills to, well, take their research to the next level. What would you recommend, Jim?
I'll just add to that, if you want to branch out into applied mathematics field, like planetary science or astronomy and so forth, then focus a lot on the engineering math courses and the applied mathematics courses. Although, the regular mathematics courses and, taking those all the way up to ordinary differential equations or partial differential equations, and especially linear algebra and things like that, those are all giving you tools for your toolbox that you can apply later. But while you're taking the course itself, sometimes you really can't see how am I ever going to apply that in the real world. But in many cases, you can. The math professors may have a tendency to talk about how they develop this in the abstract because that's their field, developing these new methods and techniques. What the fun part is taking something they developed and applying it to a real world problem. For example, there's something called a Bessel function.
Yeah.
And in my earliest work in the dissertation, I didn't have a three-dimensional terrain model like I have now, where I can numerically show the degradation of a crater. So I began with a Bessel function crater and then evolved it from a regular deep, and wide crater, and then shallowed it up and erased it that way using Bessel functions. And that's something that the math course will never, it's not going to show you how you can actually apply it in that regard. So in taking all the courses, keep in mind that there's a lot of things that you're going to learn in the math department that can actually be applied later on And part of your job as a scientist is to see a problem and realize, oh, wait, I've got that tool in the toolbox that I can apply to actually help solve that problem.
And just the one piece of advice I give to every undergrad is to go to the library or go to the journal websites and flip through the journals and figure out what are the papers you're actually interested in trying to figure out how to read. Those are the papers that you need to figure out. How do I go intern for those people in the summer? How do I learn what I need to do that research? Because in every field, there's things that are interesting and there are things that are uninteresting. I personally am not interested in dust, no matter where you put it in the universe.
Yes, I know.
And so just figure out what you do and you don't like, and then hunt down the people that you get along with, that you'd be interested in collaborating with to do that research.
Yeah. And the programming skills are especially important. So
Yeah.
I'll second your motion with regard to learning multiple programming languages and staying up to date in those regards. Because as a general rule, where the computer programming was at the time that you were a graduate student is what you tend to do in your career from that point forward, because it's very difficult to shift to a brand new programming language. I've done it in a couple of cases, but I still fall back on good old Fortran 90, 95, and even 77 and some of my programming. The kids these days are like, Fortran, what? What is that? So keep that in mind. Develop your skills and your initial programming libraries in the latest programming languages, because that will you'll be able to do some branching out later on. Just the pace of doing the research and the pace of keeping up makes it very difficult to learn a whole new programming language at some point down the road.
And that I think is really cool. Now, we also have questions coming in related to your science. Michael asks, and it just scrolled, pardon me while I get the question back. Michael asks, will the effects of the impactor that Hayabusa 2 fired at Ryugu help with the modeling?
Well, there's something called crater scaling that we do, and my model uses as well, because rather than simulate the entire process of forming an impact crater, and there's a whole branch of numerical modeling related to that called hydrocodes. Have you talked about hydrocodes with these guys at all?
No, you'll need to explain that.
Hydrodynamic codes, it takes the equations from hydrodynamic fluid flow and applies them to rocks and impacts, and actually goes through the entire process of crater formation and crater collapse, and then the ejecta that's excavated from the crater interior and thrown out the outside. Those hydrocode simulations go through the entire process. For something like my code, where I want to impact the surface with millions of impacts in rapid succession, I kind of cheat and use something called the crater scaling laws. And this is a set of equations that say, well, if you have an impactor traveling at this size with this density, traveling at this speed, and at this angle, and it impacts a target surface with these target properties, the gravity, the density, the target strength, and so forth, then this is the size of crater that you should expect to produce. And there's a branch of that goes into how much impact ejecta you will produce at the same time. I utilize all of those mathematical functions to produce my crater on the surface of the simulation. So there's a whole set of mathematical rules that we developed over going back to the 1980s, more or less, that essentially will let you scale from an impact striking a particular surface, and will tell you what size crater you will get and then how much ejecta you will produce. And then what I've added to that is how much seismic shaking you'll get as well, and that will let you rapidly simulate one impact after another, after another, after another.
So with Ryugu getting hit by Hayabusa 2's anti-tank weapon,
Thanks for directing me back to that. That gives us some ground truth for the impact crater scaling laws. Now, I think that impactor was a subsonic impactor on that body. And most impacts in the solar system are hypersonic, hypervelocity impacts they're called. So that will kind of change the scaling rules that you use, but it will help to actually say, all right, well, we hit Ryuga at this speed with this size of impactor, and since you're doing it as an experiment, you know all the inputs for the impactor, so you're just the only unknowns with regard to the target surface itself, and you can use the crater you can actually compare the prey that you produce from that to the scaling relationships and see whether they worked well or did not work very well. I actually don't know. I haven't studied that particular impact at all to know how well they work. Although I did work on the Deep Impact mission, the Comet Temple 1, and did a lot of work on that particular impact that we created there.
There's so much cool science going on with so many spacecrafts wandering world to world in the inner solar system right now. It's we can want to do research on everything, but we can't do research on everything because, well, time is short. And unfortunately, time is short also in this episode, and we're starting to run out of time. And I'm wondering, do you have any parting words that you'd like to leave with our audience?
I think I like the thing that you've hit here with, being able to pursue the science at whatever level is available to you. As an amateur astronomer, I went from just playing with a telescope in the backyard to participating in a study of radio meteors in the sky with regard to reflecting radio waves, and was able to and got to a professionally published paper with a professor at State University of New York as an amateur astronomer. So there's a lot of ways that amateur astronomers can contribute to the professional science, and just take your dream as far as you want to take it in that regard, and be very persistent and keep working at it.
Well, thank you so much to be here as an example of one of those awesome humans who did ionize from amateur astronomer to professional scientist. You're living the dream, and it's really cool.
I'm very lucky to be able to do so, and I fully realized that.
And we're lucky to have you on. And next time you have new results, I'm going to ask you back if you're willing to come back.
You betcha.
Okay. Well, I am going to let you go now and say goodbye. Thank you, Jim, so much for being with us today.
Thank you, guys.
And audience, thank you for staying here with us here on the Daily Space. This has been, as always, a production of the Planetary Science Institute, a 501c3 nonprofit dedicated to exploring our solar system and beyond. Today's episode was written by me, Dr. Pamela Gay, and our video will be produced by our own Paranor, Tim Hawkins. Things will go live later today. We are running with a few delays this week. There's some big changes, though, that we are looking forward to announcing next week. So please just bear with us while we're working on, well, making good things happen. As always, we are here thanks to the generous contributions of people like you. Your bits, your subs, your patronage at patreon.com. Well, they help us keep the servers on and our humans fed, and we really appreciate that. We kind of like to eat, sometimes too much. But these are hard times, and if things are hard for you, don't worry about us. We can take care of ourselves, and we're here for you as well. Just join us over on Discord. Find a volunteer activity to be part of, join in a science conversation, or just hang out and play some games. We're good for that. Anyways, this has been the Daily Space. We will be back tomorrow. I think this is all the streaming that we have for today. I am now looking for a channel to raid. If you have any suggestions, I am open to any suggestions. I'm not seeing anyone live right now on our standard list, but I think we're also having a tech issue with our standard list. So please send me your recommendations on who to send the audience over to next. Oh Bother is live. Okay, so we are going to raid Oh Bother. So, one moment while the tech does its thing slowly, maybe? Hello, tech. Are you going to do anything, tech? The tech is unsure if it is going to do anything. All right, so I'm just going to say thank you. Thank you for being here. And wherever you are in the world, have a fabulous morning, evening, or afternoon. Wash your hands. Wear a mask if you leave your house. And if you can, Just stay in place, and we're all going to get through this together. Thank you.